We looked at there are different ways that a function could be discontinuous at a value x equals a. But there's a special discontinuity, which is called a removable discontinuity. So depending on why it's discontinuous at that value, depends on if it has a removable discontinuity or not. So a removable discontinuity well, these happen when you have an open circle at that value x equals a. And if we have an open circle there, that limit exists. It's approaching, in our case, we can call this L. The problem is that this is not equal to, let's see, this is equal to L. Our problem in this case is that f of a doesn't exist. But if we now say, okay, let's maybe our function by is equal to this function f of x at all values of x except for a. And then we defined at x equals a, we defined it as a point. So if I say, okay, well, in order for this to be continuous here, I could just fill in this point. And so we can say when x equals a, our y value is L. And if we do that, now we've made it so it's continuous everywhere. We removed that discontinuity. This is the only type that we would have a removable discontinuity. If there had been some jump in the graph, we cannot do that. Or an asymptote, we couldn't remove it. Okay, so let's look at some examples where we're given the function and then we're trying to define where it's discontinuous. So what values? So let's say we have f of x is equal to x all over x plus 1. So it's a rational function. Rational functions are continuous everywhere where it's defined. And so I'm looking at this rational function and I'm looking at the domain and I see that there is a value of x that I have to exclude from my domain. So recall values that are in our domain, if we plug them back into our function, has to give us a real number. And I notice because we have a rational function, we have to worry about values which set our denominator equals 0. So x equals -1 is not in the domain. And recall that graphically, if you have a value of x which sets the denominator equals 0, it cannot also set the numerator equal to 0. That was a vertical asymptote. So we have a vertical asymptote. At x equals -1. And so right here, I can tell that it's discontinuous there. And one of the things that doesn't hold is f of -1. If I looked at f of -1, it doesn't exist, right? So here's one condition. It has to exist in order for it to be continuous there. So therefore, f of x is discontinuous at x equals 1. And because it's a vertical asymptote there, I know I cannot remove it. It's a non-removable. Discontinuity. Really, from college algebra, we should be able to graph this pretty fast. If we look at it, we have a vertical asymptote at -1. Recall to figure out horizontal asymptote, you look at the degree of the numerator denominator. They're both the same. So that means there is a horizontal asymptote and it's at the leading coefficient of the top and the bottom. And we just saw that we had this vertical asymptote here. Let's see where it's at crossing the x-axis. It's going to be at 0. Only place that it crosses. And we know that this is going to be hugging this line. This could technically come back up here, and it can cross a horizontal, but not a vertical asymptote. So it technically could come up here, but I doubt it. I could check it really quick by plugging in a number in between 0 and -1 to see if I get back a positive or a negative y value. So if I put in -1/2 here for x, I get -1/2 in the numerator, all divided by -1/2 plus 1, which is 1/2. That's -1, so it's down here. So I know what it looks like on this side. And then on the other side of x equals -1, that vertical asymptote, I know it's not crossing the x-axis here because I found the only x-intercept. So if I choose a point, my guess is the graph is going to look like this. If I choose a point to the right of -1, left of -1, I would get a positive number. So let's just try it. Let's say -2. If I plugged in -2 wherever I saw an x, I'd get -2 all over -2 plus 1, which is -1, which is 2. And knowing where the asymptotes are, I can tell exactly what's happening to the graph then here. So that was just kind of a quick review of graphing. We'll talk more about horizontal and vertical asymptotes later on in this section, or chapter, I believe. Okay, so it's on a non-removable discontinuity at x equals -1. So what about another example? But this time, f of x is equal to x squared all over x squared plus 3x. Okay, so rational functions are continuous everywhere, but values what set the denominator equal to 0. And so first thing I would go through is I would look to see if I can factor the denominator, which we can. So notice there's an x in common in the denominator that we can pull out. So if we factor out an x, we get x plus 3. So before we start canceling like factors, we have to exclude all values what set the denominator equals 0. So x cannot be 0, and x plus 3 cannot be 0, so that means x cannot be -3. So I know that if there's going to be a discontinuous here. But notice that I have like factors in the numerator denominator. And so vertical asymptotes only occurred with values that set just the denominator equals 0. And so look at x equals -3. If I plug this back into my original function, plugging that into the numerator is not going to give me 0. So I know x equals -3. And this one is a vertical asymptote at x equals -3. And x equals 0. So x equals 0. X cannot be 0. If I plug in 0 in here, that also sets my numerator equals 0. So this is not a vertical asymptote. This is actually a hole in the graph. And remember, if it's just a hole in the graph where it's undefined, we can remove it. So this would be a removable discontinuity. So if you really wanted to figure out what that point would be, simplify your like factors in the numerator denominator. So notice if we do that, and one x would cancel in the denominator, and would cancel one of them in the numerator. I could rewrite this as x all over x plus 3. So if I say g of x is equal to the simplified form, x over x plus 3, and I go in and I'm saying it's discontinuous at 0. So let's plug in 0 here wherever we see an x in the simplified form and see what you get back. And so doing that, we get 0 all over 0 plus 3. And so we get 0 over 3. It's okay to have 0 in the numerator if we don't also have it in the denominator. And this is equal to 0. So the removable discontinuity, we would need to add a point, 0, 0. Okay, so we're able to do that with actually not even graphing the function.